Damasceno. He's one of the students in Euclides group, and she's going to talk about atomistic finite element method. Thank you very much.
Thank you, Professor Munir. Good morning, everybody. Thank you for coming. My name is Daniela. I'm a PhD student, and I'm developing my research under the supervision of Professor Roger Pax from Carleton University and Professor Mesquita from Unicamp. In this presentation, I'm going to show you some topics of my research and what we are trying to do and what is the problems that we are working on.
Let me see a small pointer.
Overview of the presentation. I'm going to start with the motivation and show the examples that we wanted to study and show one really the main point of my research that in the future try to mix one method that is possible to work in macro scale and in nanoscale. And then, as I said, if I want to mix one method in nanoscale and the macro scale, I'm going to give you one idea what is this method in macro scale and nanoscale, and then show what it's not working more. And show one problem that the researchers are doing, and then talking about the potential energies that I need to introduce in my method to be able to study these problems. Okay, the first topic, the motivation. We want to study the mechanical behavior of nanomaterials as graphene, and then maybe applying some problems as the graphene resonator, as you can see here. But the main point is, in the future, try to be able to study one problem that we can apply atomic finite element method that I'm developing with finite element method and work with both methods. Okay, I'm going to give you one idea what is finite element method and how it's possible to work and with the both methods. What they have in similar that it's possible to work with the both. Okay, finite element method is a numerical method for solving problems in engineering science and used to solve problems with complex shape, boundary conditions, and mechanical and material behavior. When you have a problem, first you define your problem. You define your structure. Here I have one example, really simple. And then you subdivide this problem in finite elements, as you can see here. These finite elements can be like this or this or this. You will decide this based on the problem you are working on. And then the finite element method converts this continuous equation to discrete equation in this form. Here we have the stiffness matrix that is a matrix which relates the first vector with displacement vector. This is a displacement vector, and this is the first vector. Each finite element has one stiffness matrix for each. When you assemble this kind of problem, we will have the global stiffness matrix for the system. But before this, you have just for each part. So, atomic scale finite element method share the same idea. You have a structure, but this structure, we are talking about atoms. And you decide your finite element that is possible with these finite elements, get your structure. And then you define a stiffness matrix and first vector for that structure, and then assemble the problem. You have the global global stiffness matrix and global force vector for that problem. I'm going to show you the next topic, the equations. And you will be able to see that it's a similar equation. So, atomic scale finite element method. The difference here is we can solve a problem in nanoscale because we are developing this method to study these problems, and we need to introduce the potential energy for this problem. And the finite element is the same. We use the same concept. You need to define your finite element, and then you will be able to solve your problem. Okay, AFEM system is derived from the total energy minimization. And applying Taylor series expansion of total energy around the initial configuration and for equilibrium, we get the same governance equation of finite element method. But here, we need to decide what is our potential energy. This is our first step. First, you have a structure, and you have the atoms that we are working on, and then you decide the best potential for this problem that can be solved this problem. And then we apply the first derivative and the second derivative of this potential energy, and we can get the stiffness matrix and force vector. Here, you can, this example I took from this paper, and here, what they are doing, considering this beam, and they are fixing these two edges, and applying one external force here. What they doing was, they applied atomic scale finite element on this part, and the other part, finite element method. Why they're doing this? Because they are trying to, first, save computational time, and second, the precision that they are looking for, it's here. And here they can apply atomic scale finite element method and get precision in this part and save computational time. They are doing this. Still working on develop AFEM, and I hope in the future to be able to simulate some problems like this. As I said in the beginning, I need to define my potential energy. And in my research in my PhD, we will work just with Lennard-Jones potential and then Ribble potential. Because here we need to do the program for each potential. We need to implement this. As other speakers said, Lennard-Jones potential describes the potential energy of interactions between two non-bonding atoms based on their distance of separation. We can see in this expression the energy for this potential. And also you can see in this graph the potential energy curve. In this curve, you can identify these two parameters that we have in the equation. And you give these values based on the kind of atoms that we are working with. In this position, we have the equilibrium position between two atoms. If this distance between two atoms start increase, what will happen is, on the bond, we will have a weak attractive force, and we can lose one atom. If the distance starts to be close, we will come in this direction, and we will start a strong repulsion force. This is very important for us because the examples, we are always applying external force, and sometimes we don't understand what's happening in some kinds of bonds. And it's important to us to know what's happening there. Some bonds is breaking or not, is interaction or compression. And also, other thing that's really important for us, we need to do the first and second derivative of the total energy. the first derivative of the total energy is the internal force that you can see here in this curve. And it's possible to know what is the maximum internal force that that bond can support. If the internal force is bigger than that, the bond will break. So let me go to the next topic. The next topic is I need to define my atomic element as infinite element. Considering this system, but is a chain of atoms with 4 atoms. If I want to get this kind of structure, this kind of chain, I can define my atomic element as this one with 3 atoms, or this one with 5, or others. You will decide this. But one main point in atomic scale finite element method is when you define your atomic element, all the calculations will be in relation to the central node. So all the procedures will be in relation to this atom. And you will define this atomic element based on the cutoff value. If I want to say, okay, my cutoff value is just the same value of the equilibrium position, I have just this kind of connections. One this side and one this side. But if I say, no, it's 2 times of the equilibrium position, I will connect the central nodes with the first neighboring and the second neighboring. And you will define this. How you define it? You can do you can check what is the best, the procedure of the total energy. If I consider this, and I consider this, it's very different, the procedure of the total energy. You will decide this in your example. Considering that I want to get that chain of atoms using this atomic element with 3 atoms. So the first step, okay, I will apply Lennard-Jones here, and my total energy is the contribution of this energy and this energy that you can see here. And after this, you apply the first derivative of this total energy, as you can see here. This is an external force that will be applied on the chain of atoms. And then you do the second derivative of the total energy. And you have a stiffness matrix for that element. After this, you can assemble the problem. You have this chain of atoms, and you will connect the central node in relation to each atom, this, as you can see here. And then you, and also, as you can see here, this atom and this atom are not in the problem. I will not take into account the contribution of the energy of these 2 atoms. I will eliminate the contribution of these 2. And then I will assemble this problem. Each element, this has a stiffness matrix. And I will assemble this problem and get the final problem, the global stiffness matrix for the structure and the global force vector for the structure. And then I can apply the boundary conditions. For example, here I'm fixing in X and in Y direction the atom number 1, and then I can apply external force or displacement. Other example is the 2D case. We have this structure. And then if I consider this atomic element, I'm able to get this structure. If I plug this element in each part, I'm able to get this structure. But, for example, here, the atom number 1, I need to modify this atomic element. But my basic atomic element is this one. And then I will modify. For this case, for example, the 6th one, it's this kind. What is the difference? When I do this, what's happening? My total energy will change. I will not take into account the energy of the other connections. And then I will get my stiffness matrix and the first vector for each, and then assemble the problem.
What you're doing is the calculation of the whole system we have there. So you slide what you call the element, the star here. You slide one element to the right and you calculate all the forces again. You slide one to the right, calculate all the forces in the element.
For example, here,
Yeah, so
it's this one, for example.
Right.
Mm-hmm.
So we would also calculate
For
the
this?
contributions of one element that's centered on 16, for example.
Mm-hmm. Yes,
and
yes.
on the nine.
For
So-
each.
So what you call the element is the full set, but you have to calculate the energy of this and the one that's
Yes,
set to
yes.
the left.
Mm-hmm. Yes, yes. Very well.
And you have energy contribution for each one of those 6 bonds there.
Yes, yes.
And
Mm-hmm. Yes. Mm-hmm. But in this case, we don't have some contributions yet.
Sure.
But we need to calculate for each and then assemble.
But again, there is, for instance, you showed the 2-3 term.
Mhm.
Now there is the 1-6 term. The term on the 16th term. On the
Mhm.
16th term. The 16th term, there will be another interaction between the 16 and the 23,
Yes.
which is
Mhm.
already counted as the
Mhm.
23-16.
Mm-hmm.
You divided this by 2.
By 2, yes. My stiffness matrix
no double
has
bond.
half. No double.
one more.
Yeah, sure.
Can you also work with what we call to the 37, then you can have the full saying all the elements are the same.
2 with?
37. On the other side, like
Like
the other
close
side.
to
Oh, okay. Mm-hmm.
Like close to the ring and all the elements. They do this as well?
I'm not sure. Could you repeat again? It's,
Yeah.
no, it's possible, but for now, I'm just not connected. Yeah. So this was one idea using Lennard-Jones, how we can get the energy for that kind of atomic element. The other potential that we are working with is the Ribble potential. The Ribble potential is based on the Tsarov potential and describes the intermolecular interactions in carbon and hydrocarbon materials. The expression for this energy is this one. And this is the function, the cutoff function that we say, okay, we have the connection between 2 atoms or not, based on the distance of separation. And you have this part that is the proportional part and the attractive part, and this term B that connect one atom with the other 2, based on the angle between them. For this case, we are able to study the graphene sheet, for example. And considering this structure, the basic atomic element is this one. We have the central node and more 9 nodes. And so, but in some parts of the structure, we need to modify this atomic element, as you can see here. We have different kinds. It's the same atomic element, but with not considering some contributions. So in Lennard-Jones, it's easier to see what is. I will not take into account this energy contribution, but here in Ribble, it's more complex, the problem. How you say, okay, we don't have the contribution of just this connection. What will change? Where I need to study and eliminate the contribution. In the term B, that will connect this atom with these other 2, based on the angle separation, that will change. Considering this example, I have the connection between the atom 5, 1, and 8, based on this angle. And then I have the connection between 1, 5, 1, 5, 1, and 2, based in this angle. But when I come here and see 1, 5, 7, and then 1, 5, I don't have the 6 one here. I will not take into account this part in my calculation. And here you can see the comparison between AFM and MD of the total energy for these kind of elements, and they have a good agreement. What is very important in this part, because all our calculation is from the total energy. If we are not taking out this kind of contribution, our final calculation will have mistakes.
So, what is this MD variable? I lost this.
I get these results for this atomic element from MD and from AFM. And then I calculated the total energy for this kind of element from MD and from AFM.
Yeah, that's what does MD mean? So it's a Lamb's variable.
Yeah,
Okay,
yeah.
The one on top is just the term?
I'm applying the MD to study this problem using the Riemann potential.
Okay, and compared to
And comparing with AFM, yes. Numerical results now. Now using Lennard's potential and solving this problem, I'm fixing in X and Y direction the atom number 1 and apply external force in the atom number 7. Here you can see the comparison of AFM with MD. Comparison of external force by strain from MD and the AFM. You can see here a good agreement between both methods. And it's possible to see here too, what is the number of interactions it's necessary for AFM, for each external force. It's like for the maximum external force, it's 8 here. And the MD, it took 10,000 interactions. Here you also can see the relative error. And the convergence of AFM goes to 0 for the maximum force. This example is just to validate my AFM with MD. The other example is we are fixing these 3 atoms and applying external force here. Here you can see the final position of these atoms for the maximum force. And here we can see the comparison of external force by strain from AFM and MD, and the convergence of AFM when we apply the maximum force.
I guess this arrangement explain why you don't use a periodic boundary condition, because you fix one side and you apply a force on the other side.
Yeah, in MD I'm doing the same. I'm not considering periodic boundary condition there, and I'm fixing and applying external force. Other example, it's the same example, but I'm applying external force in this atom. And here you can see the final position for the external force. And also, you can see here, in this bond between the atom 37 with 34, that this bond is in compression, as you can see in this graphic, when I'm increasing the external force. And this bond is interaction, as you can see here. And also you can see the comparison of external force by strain from AFM and MD, and the convergence of AFM. My acknowledgements to CAPS and PK, CEPID, and everybody. Thank you.
I have one question.
Yeah.
In your last slide, I think it's just the compression I understand, but the traction I don't understand. Because to me it's still repulsion.
This part?
Yes, when I look at the graph,
Mm-hmm.
the red is compression, I can see the
Mm-hmm.
derivatives.
And repulsion.
Huh? Compression, right?
Mm-hmm.
There's a repulsion.
Mm-hmm.
But the traction, the blue curve, the blue part,
Mm-hmm.
the blue part, so I look at the graphics. Traction?
traction because I'm increasing the distance of between this atom with this atom.
But that's still in
When
the
I apply
repulsive
it first.
part. But it's still in the repulsive part of the potential, right? No?
But it's in, no, it's still here, in this part.
So isn't that
Mm-hmm.
repulsive? Repulsivo?
But, like, I'm increasing this distance, and so I will have a weak attractive force at this part, and we call this traction.
Yes, but that's the, I understand what traction,
Mm-hmm.
I understand. But the problem is that this part here seems to be that it's not attraction, não é atrativo.
It's a repulsion, this part.
É ainda repulsivo.
Oh, okay.
Because it's attractive to the right of the minimum.
And so, I mean, this graphic, it's because this graphic.
Isso.
And I'm calling this from this point.
Repulsion. From the minimum,
Retraction.
see?
Mhm.
From
No, it's,
here,
mm-hmm.
repulsion.
Yeah.
From here, attraction.
Yes.
But in the last slide, you are drawing this line here, not through the minimum, but through zero.
Let me see. Okay, I see.
The vertical line.
Mm-hmm. Okay, thank you.
So there is
I did.
something.
I will think about. Okay.
The
Questions?
minimum energy is after the end of the G line. This is the right side.
Ela ainda está do lado do repulsivo.
I see. I think maybe how I'm trying to show
You
it's not.
just got the drawing,
Yeah.
the drawings.
Okay.
The
Okay.
drawing is that.
Okay. Thank you.
Further questions? If not, thank you.